This is Homo habilis. She, or someone very like her, is our direct ancestor. She lived 2 million years ago. To get back to her time, you would need, on the same scale of pacing, to go about 2 kilometers, quite a long way. Now, we've got some more ancestral portraits, and I'm going to call them up in order. So will the person who's sitting behind Australopithecus, the first one, please stand up? Thank you. That's Australopithecus. He is probably a direct ancestor of this one. He lived about 3 million years ago. So we'd have to walk 3 kilometers to get to his time. Now the next person, please. Thank you. That's Ramapithecus. That would be possibly an ancestor not just of us, but also of all the great apes. And he's about 14 kilometers away on our scale. The next one, please. Thank you. That's an early primate. And to get to that one, you'd have to walk to about Hemel Hempstead to get to the age of that creature. The next one, please. An early mammal, about Luton, that distance. Next one. An insectivore with the little millipede in its jaws. Maybe Newport Pagnell. The next one, please. That's an early mammal-like reptile, and its distance is about Manchester. The next one. An amphibian. Middlesbrough. And the next. Right, that's a fish just coming out of water, just leaving the water and coming to the land, and its distance is about Carlisle. And I've left, do sit down now, thank you very much. Those are all your ancestors. This one is the oldest of all the ones we've got here. It's about the same age as the trilobite that we started with. They might have met. This is Pikaia, and in order to find its age, you would have to slog it out all the way from here to Glasgow. And remember that our perception of historical time, back to the mists of antiquity, is a couple of paces across this green table. And even with Pikaia, we haven't finished, because there are lots and lots more ancestors before Pikaia. If we go back to the origin of life, to the first bacteria, we're going back 3,500 million years. And in order to pace our way back to that age, we would have to march all the way from here to Moscow. These are the sorts of ages that we have to understand if we're going to understand evolution, and our brains are not equipped to do so. And when we were looking at our ancestors around there, we could be misled because it gives the idea that evolution is marching inexorably towards a climax, the climax being, of course, us. And that's not the way it was. Evolution was marching in thousands and millions of different directions at once. This here is not the Royal Institution Christmas tree. It's the Tree of Life, and it's a representation of a tiny, tiny fraction of the lines of evolution that there were. The origin of life is down here. This is the first 1,000 million years of life here, coming up here. Now, each of these branch points represents an ancestor of whatever lies up the branches from it. So, for example, these, there are the plants. This, I should say, is definitely not to scale. I've just noticed, so never mind that. Forget everything about scale on this tree. What is correct is the order of branching, but not the detailed distances of the branches. So this branch represents the plants. Those two are closer cousins of each other than they are of that one. This branch represents the primates with a gorilla and a human, and their common ancestor is there. This branch here represents carnivores, and there's a branch with a lion and a tiger, and their common ancestor there, which is more recent than the common ancestor of the bear and the dog, but that's the common ancestor of all the carnivores. Here we have the zebra and the rhino, not to scale, and you can see that they are more closely related to one another than either of them is to these cloven-hooved animals, the bison, the sheep, and the goat. The sheep and the goat have a very recent common ancestor. They're cousins. The bison has a slightly older common ancestor. Here we have two insects, a fly and a grasshopper. They have an ancestor there, and then they share an ancestor with the spiders a little bit earlier on. This is a tiny fraction of the number of animals and plants that there should be on this tree. This tree should have some 10 or 20 million twigs around there. And the ancestors of all these animals are in the middle of the tree, going inwards like that. So all the ancestral portraits that we've just seen around there, they would be laid out along there. What we're looking at here are all modern animals. All those animals are cousins of one another, and they're cousins of us. These hamsters here are also cousins of us. Everything that's alive today is a cousin of us. These fish are our cousins. These elephants, these are, by the way, extinct elephants, are our cousins. This swift is our cousin. We know that they're all our cousins because we know that they all have the same DNA code. The DNA code of all living things alive today is the same. And that is too improbable to have come about unless we have an ancestor. We're all descended from one remote ancestor which lived probably between 3,000 and 4,000 million years ago, and we are therefore all cousins. If we ever meet life from another planet, the creatures from there will not be our cousins. They will have evolved entirely independently. They won't have DNA, would be my guess. However, I would be prepared to say that they are likely to have quite a lot in common with us simply because there's a lot of similar problems to be solved in living, and those problems are likely to be the same all over the universe. So although they won't have DNA, they'll have something very similar in function. It'll do something very like DNA, and it'll work in a similar way to DNA. I'd also be prepared to put my shirt on the bet that they will have evolved by the equivalent of Darwinian natural selection. If we're ever visited by life forms from another planet, they will certainly have evolved the power to think and do science. Otherwise, they couldn't have got here. And their science is bound to be essentially the same as our science. This is because the principles of physics and chemistry are the same all over the universe. They'll have the same values of the constant pi as we have. They'll have Pythagoras' theorem. They'll have relativity, although they won't attribute it to Einstein. They'll probably find us pretty childish, but they'll be quite kind about our science. They'll pat us on the head and say, well, what you know about the universe is pretty much correct. You've got a lot to learn yet, but you're doing fine. Keep it up. That's what they'd say if they were talking to our scientists. What if they were talking to our best lawyers or literary critics or theologians? I doubt if they'd be so impressed. They might be their anthropologists, the equivalent of their anthropologists might be interested in us, but they would be bound to notice that our cultural beliefs are very local and parochial, not just by their standards, their universal standards, as they certainly would be, but even by our own standards. Because what people believe on our planet depends so much on whereabouts on the planet they happen to be born, which is a fairly odd thing. The Adam and Eve myth is believed by a lot of people in certain parts of the world, but if you go to other parts of the world, you'll find them believing very different myths. This is a Hindu myth, which is also very beautiful, and there are other Hindu myths as well. This is another Hindu myth of churning the milk of the ocean with a churn, gods and demons churning an axle with a turtle on the bottom, and out of the ocean came, as butter comes out of milk, came all living creatures. These creation myths are very beautiful, but they're all different from one another, and they can't all be true. And it's very odd if people believe simply what the other people in their own country happen to believe just because they're in that country. Look how scientists handle their disagreements now. Take a particular disagreement. Why did the dinosaurs go extinct?